Hello everyone, today I'm going to do Advanced Robotics Assignment E presentation. The title is Teleoperated Robot Control Using Human-Robot Interface with Implementation of a Cloud Computing Vision-Based Navigation Assistant. Let's move to the introduction part. First one, Intuitive High-Level Human-Robot Interface HRI in order to command complex manipulation tasks to a service robot. Affordable mobile devices or everyday life is focused on the HRI hardware, the benefit of utilizing a touchscreen gadget for commanding robots, as intuitive feedback is provided by displaying video stream from the robot on the screen. A minimalistic graphical user interface GUI designed and standards is applied to direct the operator decision with respect to the real-world state as is perceived by the robot. Then cloud computing is a licensing technology for robotics, particularly for mobile service robots. Another very encouraging field is that related with multi-robot cooperation at various levels, when new cooperation algorithms are being created, like multi-robot confinement and mapping slam, map consolidating obtained by a few robots, organized data achieved for robots, amongst others. Higher robotics level like object detection and recognition, gesture recognition, etc., which must run in the cloud for the image captured by onboard camera, or decision must be made by a human operator over the robotic system, or basically teleoperate the robot itself. Then you can see that this is the bill of material of my design. It contains several components such as humanoid robot, loading, adjusting, or DRL equipped with stereo camera, desktop computer with AMD Phenom 965 x4 CPU, and any model of Android tablet, OpenStack Havana, and robotic software framework ROS. The costs are listed, and the total cost of the design is $10,099. Then I will discuss technical principle. First is cloud-based navigation assistant for the teleoperation of the mobile robot. The rolling adjusting robot carries a stereo camera which sends frame to the teleoperator and to those processors responsible for 3D point cloud 3D PC extraction. Once a 3D PC is obtained from a stereo frame pair, it is sent to a navigation assistant node. This navigation assistant node will also receive input commands from the local command interface, a virtual handles on tablet, which are translated to the desired linear angular speed with omega z. The navigation assistant will be able to calculate the correct max that avoids an obstacle collision with the previously received obstacle information. There is the 3D PC and the historic buffering of robot velocities. Second one is time diagram of the system. Time diagram of the system camera all captures a frame pair that sends it to the point cloud extraction C. This extracts the 3D PC and sends it to a navigation assistant which fuses this information with the user command coming from the virtual button Z. Finally, the actuators U receive the velocity commands. Different interval times increment the total latency of the system. When working with real-time navigation, analysis over the average latency is required. Most of the latency comes from the time the system taps to process the virtual information. The robot's onboard computer comprises the stereo camera O and the motor actuation subsystem U. Is case of delay correction in distance to correction X calculation. First, the effect of this oscillation are mitigated or encountered by the user because she is conscious of this kind of problem when remotely driving a slow robot. Second, some delay correction have been incorporated in the actuation subsystem. As the information obtained from the stereo camera is delayed, obstacles are actually nearer than the correct case. Let us suppose that the system calculated at tk plus 1 that an obstacle is at sk meters. Due to the timing latency, the robot is actually closer. To be conservative, we have supposed that during this latency time, the robots have moved at the maximum speed asked by the user. Therefore, a simple predictive correction consists of subtracting sk an estimated distance etc. equal to Vz times Z, where T equal to Tk plus 1 minus Tk. Then the technical principle is information providing algorithm. An intuitive UI is needed to command flexible manipulation tasks to a service robot in a compelling way. This issue is approached by integrating the interval world state of robot into an object-centered UI. The entry point for the operator is thereby not task specified but the selection of a single object or set of multiple objects, allowing our approach to scale for arbitrary tasks. A list of all selected objects is passed to the list action function described in algorithm 2.1 that identify all available action changes for the chosen object. And for the next one, algorithm 2.2, first all available action templates are created by iteratively calling the getAllActions function for all objects of interest. This includes all actions for the particular object class and all parent classes. In the second loop, all object classes, respectively object parent classes, are substituted at their first appearance in the action. See substitute parameter. The resolve action function is executed for each action given by algorithm 2.1. To cover all action possibilities, the world state is recursively passed for all available parameter combination by the recurse parameter function. All not yet substituted parameters are therefore iterated and listed according to the current world state. Then let's talk about overview of software components of the prototypical HLI. The UI provided by the mobile devices require only few continuous input from the robot, compressed video stream, selected telemetry data, and current world states. CAD data for the visualization of world state objects is downloaded from the RobotView cloud system and cached at the mobile device on demand. The commanding of the robot is done by transmitting PDDL action description from the mobile device to the robot. The application requires little bandwidth due to the transmission of few selected and compressed data. Furthermore, higher latency of the overall system is tolerated by shared autonomy compared to a teleoperation approach using the mobile device. The operator interacts with the object in the world state of robot. The respective CAD models are rendered on top for the live video stream. A set of possible actions with respect to the selected object is generated from the symbolic world state and presented to the operator using a link menu. Lastly is the element of sustainability. Humanoid robots can reduce human resource and they can perform more than one task than human being. This will improve also efficiency of communication and high efficiency than human being. Besides that, they also can have more interaction with human. Thank you everyone for listening. And that's all for my e-presentation. Thank you.